Good day everyone and welcome. I'm excited to present our research titled Multi-View Action Recognition via, authored by Gromov-Wasserstein Directed Gromov-Wasserstein Discrepancy, Tan, Dat Nguyen, Koa Trong, and Liu. We've delved into the fascinating world of action recognition, specifically tackling the challenge of camera angle variations. Our work introduces a novel deep neural network model that not only recognizes actions, but also considers different camera views for more robust and consistent results. Stay tuned as we unravel the intriguing details of our research. In this slide, we delve into the key highlights of our research. The primary motivation behind our work is to enhance the robustness and accuracy of action recognition in videos. We aim to achieve this by considering different camera angles. This approach is inspired by how humans perceive and understand actions in real-world scenarios. We naturally adjust our understanding based on the viewing angle, and we believe our model should do the same. Our goal is to ensure that the model's attention remains consistent across different views. This means that even when the camera angle changes, the model's focus on the action subject should remain steady. This consistency is crucial for making accurate and reliable predictions. In essence, we're trying to make our model perceive actions in a way that's more aligned with human cognition. By doing this, we hope to significantly improve the model's performance in action recognition tasks. In this slide, we delve into the key highlights of our research. We address two main problems. The first one is the challenge of inconsistent action recognition results due to variations in camera angles. This is a significant issue in the field of computer vision, as the same action can appear different when viewed from various angles. Our proposed method aims to ensure that the attention of the model is consistent, regardless of the camera view. The second problem we tackle is the issue of explaining predictions produced by deep neural networks. As we know, deep learning models are often seen as black boxes. Due to their complex nature, our work aims to make these predictions more understandable and transparent. We do this by visualizing the regions of the model that give attention with respect to the predictions. In essence, our research is about improving the robustness and accuracy of action recognition models by ensuring consistency across different views and providing clear explanations for their predictions. In this slide, we delve into the key insights of our research. Firstly, we found that taking into account the camera angles can significantly enhance the accuracy of action recognition in videos. This is a crucial step forward in the field of computer vision. Secondly, we've introduced a novel concept: attention, consistent similarity computation. This concept allows us to measure the similarity between attention maps from different views of a video, ensuring the model's attention to the action subject remains consistent even when the view changes. Lastly, we've emphasized the importance of maintaining motion features in action recognition. This is achieved through our proposed direction information approach, which retains the motion features while computing the Gromov-Wasserstein distance. These insights are pivotal in our quest to improve the robustness and accuracy of deep neural network models for action recognition. Moving on to the key highlights of our work. Our first major contribution is the introduction of a novel multi-view attention consistency method. This method utilizes Directed Gromov-Wasserstein Discrepancy to explain action recognition. This discrepancy not only measures the similarity between attention volumes from different views, but also preserves the motion information and structure of the compared attentions. Our second key contribution is the proposal of a new metric for multi-view attention consistency. This metric is designed to ensure that the attention of the model remains consistent even when the view of the video changes. Lastly, we have developed an action recognition model that leverages the ideas of video transformer and neural radiance fields. This model allows us to obtain attention from different views, enhancing the robustness and accuracy of action recognition. In essence, our work is a significant step towards improving the reliability and interpretability of action recognition models. In this slide, we delve into the key highlights of our proposed method. We start with the main idea, where we map an input video and camera angle to an action prediction and a spatial temporal attention volume. This is a crucial step in our process as it allows us to classify actions and define a metric that computes the consistency between the attention volumes of the model from different camera views. Next, we utilize a video transformer as the backbone of our structure. This powerful tool allows us to compute the feature volume of an input video, which is essential for our method. We then employ neural radiance fields to obtain attention volumes from different camera views. This approach helps us reduce computational cost and increase efficiency without compromising on the quality of our results. Finally, we introduce an attention-consistent similarity computation using Directed Gromov-Wasserstein Discrepancy. This innovative approach allows us to compare the structures between two attentions, ensuring the robustness and accuracy of our model. In summary, our method combines these key components to provide a robust and efficient solution for action recognition. Stay tuned as we delve deeper into each of these components in the following slides. In this slide, we will highlight some key results of our study. Firstly, our model has shown robustness to different camera angles. This is a significant achievement as it allows for more flexible and diverse video data collection. Secondly, we compared our model's evaluation results on the Kinetics 400 and something V2 datasets to prior state-of-the-art methods. Our model outperformed these methods, demonstrating its superior performance. Lastly, we found that the performance of our action recognition model was notably improved by using the proposed directed Gromov-Wasserstein loss. This loss function played a crucial role in enhancing the model's accuracy. These results underscore the effectiveness of our proposed method in action recognition tasks. In this slide, we delve into the motivation behind our method. As you can see in the figure, our goal is to ensure that the model's attention remains consistent across different camera views. This is crucial for our work in the field of automatic action recognition, a fundamental research problem in computer vision. This problem has wide-ranging applications, from surveillance and video information retrieval to scene understanding and human-robot interaction. By ensuring consistent attention, we aim to improve the robustness and accuracy of our model, particularly when the view of the video changes. This approach is inspired by the natural visual perception of humans, which remains consistent despite changes in viewing angle. In this slide, we delve into the motivation behind our method. As depicted in the figure on the right, our primary aim is to enhance the robustness and accuracy of action recognition. We strive to achieve this by ensuring that the model's attention remains consistent across different camera views. This consistency is crucial as it allows the model to maintain focus on the action subject, even when the view of the video changes. By doing so, we can ensure that our model produces reasonable and reliable predictions, thereby improving its overall performance in action recognition tasks. Begin a frame. Frame title. Our proposed method. Begin a mini page. T is 0.5 line width. Begin itemize. Item. Our method involves using a deep neural network to classify actions in a video, while also defining a metric to measure the consistency of attention volumes from different camera views. Item. We utilize the video transformer for the fundamentals of our approach and the neural radiance fields for attention volumes in different camera views. Item. We also propose an attention-consistent similarity computation using the Directed Gromov-Wasserstein Discrepancy. End. Itemize. End a mini page. Hfill. Begin a mini page. T is 0.5 line width. Begin a figure. Centering. Include graphics. Height equals 0.8 text height. SRC task underscore execution. Extracted underscore paper underscore data. 2405.01337v1 figures. 2405.01337v1 figure 2:1.png. Caption illustration of our proposed method. The figure shows how we use a deep neural network to classify actions and measure the consistency of attention volumes from different camera views. End of figure. End a mini page. End a frame. In this slide, we delve into the motivation behind our proposed method. As you can see in the figure, our goal is to ensure that the model's attention remains consistent across different camera views. This is crucial for accurate action recognition in videos. However, previous solutions have had their limitations. Techniques like class activation mapping and grad cam, which visualize attention regions, struggle with variations in camera angles. They may not be robust enough to handle different views, leading to inconsistent recognition results. Our method aims to overcome these limitations by focusing on the consistency of the model's attention, regardless of the camera view. This approach is inspired by the natural visual perception of humans, which remains consistent despite changes in viewing angles. By adopting this approach, we aim to improve the robustness and accuracy of our deep neural network model for action recognition. Moving on, let's delve into the crux of our proposed method. As you can see in the figure on the right, our primary motivation is to ensure consistent attention of the model across different camera views. This is crucial in handling variations in camera angles, a common challenge in video analysis. Our approach to this problem is twofold. Firstly, we aim to measure the similarity between attention maps generated from different views. This allows us to understand how the model's focus changes with the camera angle. Secondly, we use a unique metric that compares the structures of these two attention maps. This comparison helps us quantify the consistency of the model's attention across different views. In essence, our method is designed to provide a robust solution to the camera angle variation problem by ensuring the model's attention remains consistent, regardless of the camera's position. This approach opens up new possibilities for action recognition in videos, making it more reliable and accurate. Begin a frame. Frame title our proposed method. Begin a mini page. T is 0.5 line width. Begin itemize. Item our method involves an input video, represented by X, with dimensions corresponding to the number of frames, height, and width of the video, and the moving angle of the video camera, represented by beta. Item, we aim to learn a deep neural network to classify actions and define a metric that computes the consistency between the attention volumes of the model from different camera views. Item, we utilize the video transformer for the fundamentals of our method, and the neural radiance fields for attention volumes in different camera views. Item, we propose an attention-consistent similarity computing method using Directed Gromov-Wasserstein Discrepancy. End itemize. End a mini page. H-fill. Begin a mini page. T as 0.5 line width. Begin a figure. Centering. Include graphics. Height equals 0.8 text height. SRC task underscore execution extracted underscore paper underscore data. 2405.01337v1 figures 2405.01337v1 figure 2:1.png caption illustration of our proposed method. This figure shows how we use the video transformer and neural radiance fields in our method. End a figure, end a mini page, end a frame, backward. On this slide, we delve into the crux of our proposed method. As you can see in the figure on the right, our goal is to ensure consistent attention of the model across different camera views. This is crucial for accurate action recognition in videos. Now, how do we achieve this? We leverage the power of Neural Radiance Fields, or NRF. This technique allows us to render information from novel views. The beauty of this approach is that it enables our model to obtain attention from multiple views, even when we only have single-view videos. In essence, we're teaching our model to understand the scene from different perspectives, enhancing its ability to recognize actions regardless of the camera angle. This is a significant step forward in the field of video action recognition. Moving on to related works, let's first understand the role of action recognition in computer vision. It's a fundamental research problem with applications ranging from surveillance to human-robot interaction. The rise of deep neural networks has significantly advanced this field, with many successful applications in action recognition tasks. Now, let's delve into some existing approaches. Class activation mapping, or CAM, has been instrumental in visualizing attention maps, providing insights into areas where the model focuses. CAM further enhances this by producing attention maps through backpropagation, combining gradients with forward features for a more comprehensive understanding. Lastly, we have the transformer model. It's a game changer in the way it uses self-attention weights for visualization, providing a unique perspective on how the model processes and understands information. These methods have been pivotal in our understanding of deep learning models and their predictions. In the next slides, we'll explore how we can build upon these foundations to improve action recognition. Begin a frame. Frame title our proposed method. Begin itemize. Item introduction to our method. We propose a deep neural network that classifies actions and defines a metric for consistency between attention volumes from different camera views. Item video transformer. We utilize the fundamentals of the video transformer to handle video inputs. Item neural radiance fields. We employ neural radiance fields for attention volumes in different camera views. Item attention consistent similarity. We propose a novel method for computing similarity using Directed Gromov-Wasserstein Discrepancy. Item model evaluation. Our model, trained using directed Gromov-Wasserstein loss, outperforms other candidates with a top 1 accuracy of 83.49% and a TOP5 accuracy of 96.17%. End itemize, end frame, .. In this slide, we delve into our proposed method. We've developed a deep neural network that not only classifies actions, but also measures the consistency between attention volumes from different camera angles. We've incorporated the principles of the video transformer for handling video inputs and used neural radiance fields for attention volumes across various camera views. We've also introduced a unique way to compute similarity using directed Gromov-Wasserstein discrepancy. Our model, trained with this method, has shown promising results, outperforming other candidates with a top 1 accuracy of 83.49% and a TOP5 accuracy of 96.17%. In this slide, we delve into the related works that have shaped our research. Firstly, we look at multi-view action recognition. While there are datasets available for this, they often come with limitations, primarily being recorded in controlled lab environments. We believe there's a need for datasets that reflect real-world contexts, even if they are single view. Next, we explore the Gromov-Wasserstein distance, a metric used in image matching. It's a powerful tool for comparing topological similarities between images. However, it has a significant limitation when applied to action recognition. It doesn't account for the motion of the subject, a crucial aspect in our field. These related works have informed our approach, but also highlighted areas where we could innovate and improve. Stay tuned as we delve into our novel method in the next slides. Moving on to the technical details of our proposed method, let's take a closer look at the illustration on the screen. This diagram represents our proposed action classification model. The model processes the input video through several stages. First, the video is decomposed into patches. These patches are then embedded and computed via transformer blocks. The output is then mapped into the weights of a multi-layer perceptron in the feature renderer. The final feature vectors produced by this process are used for classification. Now, let's break down the key aspects of our proposed method. Firstly, we propose a deep neural network model specifically for action classification. This model is designed to consider camera angles, which is a unique aspect of our approach. The model maps an input video and its corresponding camera angle to an action prediction. In addition to this, it also generates a spatial, temporal attention volume. This attention volume is crucial as it helps us understand where the model is focusing its attention during the action recognition process. This way, we can ensure that the model's attention is consistent, even when the view of the video changes. Let's delve into the key components of our proposed method. First, we have the video transformer, which serves as the fundamental structure of our model. It processes the input video through several stages, including decomposition into patches, embedding, and computation via transformer blocks. Next, we utilize Neural Radiance Fields, or NRF, for attention volumes in different camera views. This allows us to capture and analyze the spatial temporal attention volume corresponding to the video from different perspectives. Lastly, we introduce the use of Directed Gromov-Wasserstein Discrepancy. This is a novel approach for computing attention, consistent similarity, which helps us to measure the consistency between the attention volumes of the model from different camera views. As you can see in the figure, these components work together to process the input video and map it into the weights of MLP in the feature renderer. The final feature vectors are then used for action classification. This comprehensive approach allows us to achieve high accuracy in action prediction while maintaining consistency across different camera views. In this slide, we delve into the technical details of our proposed research. As you can see in the figure, our action classification model processes the input video through several stages. These stages include decomposition into patches, embedding, computation via transformer blocks, and mapping into the weights of MLP in the feature renderer. The final feature vectors are then used for classification. Now, let's talk about our approach. Our primary aim is to improve action recognition by ensuring the model's attention is consistent across different camera views. This is crucial because the attention of the model to the action subject should remain consistent, even when the view of the video changes. To achieve this, we measure the similarity between attention maps from different views of a video. But here's the challenge. The change in view transforms the model's attention, so we need a metric that compares the structures between the two attentions. This is where our direction information approach comes in. It maintains the motion features from Gromov-Wasserstein distance computing. This is a significant step forward because it mitigates the problem of ignoring the motion of the subject in action recognition. In other words, it allows us to keep track of the subject's movement, which is crucial for accurate action recognition. Let's delve deeper into our proposed research and technical details. As you can see in this figure, our action classification model processes the input video through several stages. It starts with decomposing the video into patches, followed by embedding. The computation is then carried out via transformer blocks, and the results are mapped into the weights of an MLP in the feature renderer. The final feature vectors are then used for classification. Moving on to our experiment design, we tested our model on 3 popular action recognition datasets: Jester, something V2, and KINETICS 400. We evaluated the performance using TOP1 and TOP5 recognition accuracy. To further understand our model's performance, we conducted an ablation study on the Jester dataset under different settings. Stay tuned as we delve into the results and insights from these experiments in the upcoming slides. Moving on to the technical results and improvements, our model has shown robustness to different camera angles. This is a significant advancement as it allows for more versatile applications in real-world scenarios. We've also demonstrated the quality of our model through various consistency losses, further proving its reliability. We've compared our model's evaluation results on the Kinetics 400 and something V2 datasets to prior state-of-the-art methods. The results were impressive, with our model outperforming others. Specifically, our model achieved a TOP1 accuracy of 83.49% and a TOP5 accuracy of 96.17% on the Kinetics 400 dataset. On the something V2 dataset, our model achieved a TOP1 accuracy of 70.74%, which is 1.14% higher than our base model. SWIN B. One of the key factors contributing to this performance improvement is the use of the proposed directed Gromov-Wasserstein loss in our training process. This innovative approach has proven to be highly effective in enhancing the performance of our action recognition model. As you can see in the figure, our proposed action classification model processes the input video through several stages, including decomposition into patches, embedding, computation via transformer blocks, and mapping into the weights of MLP in the feature renderer. The final feature vectors are then used for classification. This comprehensive process ensures accurate and reliable results. In this slide, we delve into the key results of our research. We conducted tests on 3 widely recognized action recognition datasets: Jester, something V2, and Kinetics 400. Our model demonstrated a high degree of robustness to different camera angles, a significant factor in real-world applications. We also compared our evaluation results on the Kinetics 400 and something V2 datasets with previous state-of-the-art methods. The findings suggest that considering camera angles can significantly enhance action recognition in videos, contributing to the robustness of the model. The figure you see here provides a visualization of attention across 4 frames from 2 camera angles on 3 settings. This visualization helps us understand how our model performs under different conditions. In summary, our research has made significant strides in improving action recognition in videos, particularly in terms of robustness to camera angles. Moving forward, let's delve into the conclusions and key remarks of our study. We've introduced a unique method that brings together multi-view attention consistency and directed Gromov-Wasserstein discrepancy for action recognition explanation. This method is not just about computing similarity between attention volumes from different views. It goes a step further by preserving the motion information and the structure of the attentions being compared. Moreover, we've employed neural radiance fields for implicit feature rendering. This has been instrumental in addressing the training challenges on single-view datasets. In essence, our method is a blend of innovative techniques that not only enhance the performance of action recognition models, but also provide a comprehensive understanding of the process. This is a significant stride in the field of action recognition, and we're excited about the potential applications and future research opportunities it presents. Begin a frame. Frame title at conclusions and remarks. Begin itemize. Item testing and validation of the model. Begin itemize. Item. Our model was rigorously tested on 3 widely recognized action recognition datasets. Gesture, something V2, and Kinetics 400. Item, we observed a significant improvement in performance when we incorporated our proposed directed Gromov-Wasserstein loss. This innovative approach computes the similarity between attention volumes from different views while preserving the motion information and the structure of the compared attentions. Item, the high accuracy performance of our model was further confirmed on the something V2 and Kinetics 400 benchmarks. In fact, our model outperformed other candidates with a top 1 accuracy of 83.49% and a TOP5 accuracy of 96.17%. End itemize, end a frame, In conclusion, this research has significant implications for the field of action recognition. We've shown that by taking into account camera angles, we can significantly enhance the accuracy of action recognition. This provides a fresh perspective on how to handle variations in camera views, a common challenge in this field. Our method of attention, consistent similarity computation, contributes to the robustness of the model, ensuring that the model's attention remains consistent even when the view of the video changes. This is a crucial step towards creating models that are not only accurate but also reliable. Furthermore, we've demonstrated that the cognitive processes of human perception can be adopted to improve the robustness and accuracy of our models. By mimicking how humans naturally perceive and recognize actions, we can create models that are more in tune with real-world scenarios. In essence, our research opens up new avenues for improving action recognition models, making them more robust, accurate, and adaptable to variations in camera views.